So now that we have seen what conservative forces are, we can now discuss the concept of potential energy. So recall that if your mass goes from point A to point B in some conservative field, then the work done by the field does not depend on the path taken from A to B. The work done by conservative force only depends on the initial position of the particle A and the final position of the particle B. So in other words, when you have work done by conservative force, it only depends on endpoints and not the path taken between those two endpoints. We can then define a potential energy function UR in the following way. If you have the work done along some path, any path from A to B, which is given like this, we can claim that that's equal to the negative of a change in potential energy. In other words, it's the negative of the potential energy at B minus the potential energy at A. This minus sign is useful as a definition. For now, let's pick this up as a definition. It's useful because it leads to a familiar expression for conservation of energy. So this definition allows us to set something called a reference potential. So notice something. We see that only changes in potential energy actually mean something, because this work done is a physical thing. It's the force times displacement, right? So we've seen that the work done was defined in the following way. Potential energy was defined in the following way, that the change in potential energy has a negative which is equal to the work done. But let's say this potential energy function UR is redefined in the following way. You have a new potential energy function U prime R, which is equal to the old potential energy function plus a constant. This is basically the same thing as if you have y equal to x square. The graph of y equal to x square looks like this, right? Y equal to x square. And the graph of y equal to x square plus 2 is this whole graph shifted upwards by 2 units. In other words, to every point, to every y coordinate you've added plus 2, right? It's just shifted upwards. You've done the same thing with this potential function here, right? You've just shifted it upwards by some constant. But notice that in doing so, the change in potential energy is absolutely of the same form. You see, u prime b minus u prime a is just ub plus constant, right, minus ua plus constant, which is just ub minus ua. So u prime b minus u prime a is equal to ub minus ua. That's interesting. So you can redefine this potential function by adding a constant, and that doesn't change anything to our physics because the work done is just the negative of the change, and it's only the, and that change does not change, so to speak. Now what can you do with this? So you can add an overall constant to the potential energy function without altering the changes in potential. Now you can use this freedom in the potential function, that is the fact that you can add a constant to the potential. You can use this freedom to set the potential to 0 at any point you like. You can in principle choose this point anywhere you like, but there are some common and useful choices. For example, in the next couple of videos we shall consider the potential energy of a spring and the potential energy of a gravitational field, both near the surface of the earth and in general, and we shall see how to describe a reference potential, or we shall set an unambiguous point where the potential is 0.